Swift does support types called unsafe mutable buffer pointer and unsafe raw pointer, which can hold references to an array of bytes, much like a C pointer. You can, of course, iterate through those bytes or access them randomly, but any insertions would require reallocation, and the memory rules are neither automatic reference counting nor value types. So Foundation provides a type for safely handling byte arrays, and it knows how to insert, read-write to files with URLs, transform to and from base64, has standard struct value memory semantics, and can even memory map itself from a file. It's called data. Data can be created with an array of bytes, and we can randomly access the data with the square bracket subscript operator like we would reference an array. Or we can iterate through the bytes one at a time. We can append one data to another.
Data even conforms to the random access collection protocol, so in many ways, interacting with data is just like interacting with an array of uint8s. Here we insert both a single byte and also an array of bytes at specific indices. Data also supports methods for removing or replacing specific subranges.
Usually, data will be an opaque intermediate representation between the file system and another kind of object. For instance, here it's used to read from a URL. Imagine now that we're parsing a complex format and we want to see 4 bytes that are in a data at a given index as an unsigned 32-bit integer. We don't have a built-in way to do this, so let's look at a recipe. In this generic extension on data, we get the size of the type from memory layout. We'll want to copy the bytes from a particular range in the data, and to do that, we'll need an unsafe mutable buffer pointer. So we'll create one with some temporarily allocated bytes, which we'll deallocate in the deferred block. Once the copy is done, we can use the unsafe pointer's pointee computed property to retrieve a fully assembled content type, whatever that is. To append bytes to a data, we allocate our extra bytes by making a var copy. We grab an unsafe pointer to the copied value with the withUnsafePointer method. If we had just used the ampersand operator to get a pointer, value copy would have gone out of scope before the call to append, but only when building for release, potentially crashing the app, but only when released. You may wonder, how does append know how many bytes to add? Well, the unsafe pointer is a generic and follows our POD type. Unsafe buffer pointer is different. It points to what amounts to a C array of things. It keeps track of a count property, and inside it uses the same memory layout generic to get the size of the items. Here, we're just using one. We should only use these methods with types we know to have compact memory representations, like int32s and float64, not just any enum structure class. To support efficient alignments, Swift has a tendency to insert more padding inside a struct's actual memory than C would. This means that the C technique of reinterpreting an array of bytes as a pointer to a struct won't always work in Swift. Finally, if you're a C developer, you may be wondering, why do we have to go through such lengths just to cast some bytes? Well, the answer is Swift prefers type safety, and using a type that's named unsafe by the language is intended to warn you of the ease of misuse. Fortunately, there is a way to do dangerous operations correctly, and we're wrapping those up in these extension methods, which you can now copy and paste into your own projects. If we know the data is supposed to represent a string, we can init the string with the data. Notice that we've assumed the use of a UTF-8 format, and that's a static member of the nested string encoding type, which defines many common string encoding formats like ISO Latin 1, ASCII, and Windows CP125, I'm not even sure what that is. This example also shows how to turn a string into a data with a particular encoding. Perhaps the data is actually represented in the string via a base64 encoding. We can turn that directly into data and back again. Let's revisit strings and talk about ranges. Swift strings have deep knowledge of the Unicode standard, even more so than in Objective-C. In fact, a Swift string is abstracted as a sequence of Unicode grapheme clusters, which means that each element represents a single, complete, drawable glyph. As a result, we can't construct ranges for strings with ints. We need to use strings nested index type. This example pulls a substring, which just happens to be the entire length of the original string. When we add foundation, strings gain many other abilities, such as this method, which finds the range of a string within another. When we have simple questions about the beginning and end of a string, there are easy functions for checking a prefix and a suffix. In other cases, we may want to divide a string into components divided by a specific substring, and the components separated by function does that for us. Perhaps we want to divide a file into lines and then reassemble it. We use the joined with separator function. Today we learned how to work with data. We started with byte by byte access and operations for insertions, deletions, and replacements. Then we studied recipes for working with several bytes together. We converted data to strings and strings to data using different encodings. Lastly, we took a deeper look at string ranges and divisions.
A plethora of standard string data encodings that ship with our language tools? Now that's Swift.